and sell it to 2 different applications. And that's better than having that stock increase double. So, you'll see this in the field. A multi-voltage motor, or dual voltage motor, I should say. Okay, now I am drawing the windings of a dual voltage motor, and I'm going to show you how the windings are marked. This is, like I say, pretty much of an industrial standard. I start off with T1, T2, T3. Y'all notice any pattern I'm doing? T4, T5, T6, T7, T8, and T9. Did you notice the pattern?
Clockwise.
And I kept going towards the
Going
center.
in. Yeah.
Okay? Now, how do I wire it up? Well, let's say that this motor is a 240, 480 volt application motor. It would only be one or the other. You can't have it both. But you have to wire it for one or the other. If I'm going to wire it for the higher voltage, I connect T7 and T4 together. I connect T8 and T5 together. I connect T9 and T6 together. Then I put my leads coming in. L1 would go to T1, L2 would go to T2, L3 would go to T3. If I need to reverse that motor, I swap any 2 of these incoming leads. It will change the rotation. Now, that was easy enough, but what if I need to wire it up for the 240 application? Still simple. Did you notice that that was in the windings were in series? Okay. This time I take T4, connect it to T5, connect it to T6. Okay. I just made a star just like this out of those right there. See that? Now I take T1 and T7, tie those together. I take T8 and T2, tie those together. I take T3 and T9 and tie those together.
T7 and T4.
T3 and T9.
Yeah.
Okay. All right. Now my power comes in on T1, T2, and T3. And again, if I need to reverse it, I reverse any of these 2 leads. Okay. Now it's wired for the
They all work together.
240.
They all work together. Like, I'll
Okay.
explain this. Okay, all this is motor, those 2 things are motor, right? Then the lines right here are like, they're showing like the electricity going through it.
Right. That's I'm tying these leads together.
And so it all run current.
Yeah. The current would go through this winding and this winding concurrently. Okay. Here's the leads. This is a 3-phase motor right here. Here's the leads. And if you will,
Y'all say something.
it should be numbering on here.
They say T2, T3, and everything.
Yeah, you see that?
Yeah.
See the numbers? T4.
T9, 8, 7.
Right.
I'll write it down.
Okay. Now, that is like I say. If you ask me about a 3-phase motor, I could probably answer how to wire it up, because that's pretty much of a standard. But it's the only one that I know that pretty well holds that standard. All right. Now, there's one other motor that has come into our industry over the last few years and has become very popular in some of the higher end equipment. I said that higher end equipment. You know what happens? Y'all know this is true. I like to go back to the automobile. You remember when power windows was not in every vehicle you got in?
Right.
In the vehicle nowadays, and
It's in every
Up
color.
it's just about every one of them, you know,
Up before my time.
before your time. I don't go back to that day that they had the crank in the front. But I have had ones that didn't have starters. I always had to park on a hill. But that was another problem. But you know, what we come into is the commercial and industrial side of it using three-phase motors. There was applications for AC motors that haven't been feasibly both money-wise and complicated to get multiple speed or variable speeds. What I'm trying to say is it used to be done with DC motors. Anything variable speed was done with DC motors. Well, they come up with variable speed drives. Some folks call them variable speed drives, VSD. And you also hear another term, variable frequency drive, VFD. They're the same. They're the same. Variable frequency drive, variable speed drive. They do the same thing. If you had two of them sitting in front of you, one was called a VSD and the other was called a VFD, there would be no difference in what they are. Now, this allows AC variable speed control, which opened up the industry big time. Now we can match fans to the speeds that they really need to go. We can match compressor pumps to the speed that it really needs to go. Okay? That has come over into the residential side. But the cost of these devices, well, let's put it this way. It's done like computers. It was way up here at one time. Nobody could afford them. Now, most every household has a computer. Okay? You just don't see it. It's kind of like the TVs, you know. One time, we had a TV. Neighbors did. Oh, well, that was a long time ago. Now I got a TV, never turn it on. But the thing about it is the price has come down, but the variation on it for the residential is going to be called an ECM. Okay? This is the drive for the ECM. Electrically commuting motor. This is the stator and the rotor. Okay. Now, this has a permanent magnet in the rotor. A little bit different than the industrial type of VFD or VSD, but it still does the same thing. The drive part and the motor are usually sold as one piece. At one time you could buy this separate. I think industry pretty well said, no, we're going to quit doing that. We're going to sell it all as one piece because this part can take this part out and vice versa. So they were having problems with
back and forth.
Back and forth. Okay. Well, what's that allowed us to do? It's allowed us to actually use one motor, one device for several different applications. And it can be set up in the field for the correct speeds that it needs to be running. Plus, there's something else that I didn't talk about. Inrush. By reducing the inrush or the torque needed to start up, I reduce the power usage. One of the biggest power uses is to start up a motor. For example, I may have a motor that pulls 10 amps when it's running normally, but it may take 60 amps to get it started. If I can get rid of that peak inrush, then I reduce the amount of electricity that I'm going to use. Even though it's a split second, it's still, well, let's put it this way. If I short out that receptacle right there, and basically that's what happens, I'm going to use a lot of power for nothing, right?
Right.
That's pretty much what was happening when you start up a motor. Not completely nothing, but it's the energy used to get it going. Kind of like trying to get me out of bed in the morning, you know. It takes a lot of effort to get me out of bed in the morning, but once I get going, I don't know when to quit. All right. So the variable speed, or ECM motors, as it's called in the residential field, has become very, very popular. And it's going to get even more popular. They are expensive, but what's going to happen? The more that you use, the price is going to fall. And it's already started doing that. All right. Now let's get to the starting devices. Are y'all ready for this? Y'all okay right now?
Oh, yeah.
All right. Nobody needs a break or anything? Y'all need.
I think I'm going to get some coffee. But
All right. Let's give it 10 minutes. R to S should read how much?
3. You could add, right?
Oh,
yeah, R to S,
9.
9 ohms. Okay, that's because my ohm meter on that first one is measuring through this winding right here. The second time I'm reading through this winding. The third time I'm reading through both windings. See that? Okay, what if this was open? R to C would read what?
0.
Infinity.
Right.
Okay, not 0,
Oh,
infinity.
yeah.
Okay. Okay, S to C would read what?
Infinity.
Infinity. R to S would read what?
No,
No.
no, 3,
9.
9.
Because I'm measuring here,
Right.
I'm going through that device. Okay, that's how you can tell if you got open overload.
The infinity reading is when the gauge just keep jumping from numbers to numbers and it.
It's usually OL.
It's
open
overlaid
lead.
because it's a potential relay. I started messing it up.
Okay. Now, if I do this like I'm adding it up, I want you to look at this. Okay. This is C, this is R, and this is S. So my ohm readings from here to here, and my ohm readings from here to here should add up to the ohm readings from here to here. Does that make sense? That's one way that you can electrically check a motor with an ohm meter. Does that mean it's good?
No.
No. But it means that the windings are not shorted. There is not a turn-to-turn short within it. They're not open. That's all it means. Now, if you had a situation where this one read 4 ohms, and for some reason or another you still had 9 here, you may actually have a short within it or something of that nature. Okay? In other words, if they don't add up, there's something wrong. Now, if I'm checking to the ground, okay, the case or the ground, I should get infinity. If I get any reading, especially anything above about 150,000 ohms, be suspicious. I'd be very suspicious of 150,000 ohms.
What would you be suspicious of?
Shorted to the housing. Somewhere in that housing, this winding's probably touching the metal piece. Okay? Or somewhere is touching the metal piece. I say there are certain refrigerants and certain oils under certain conditions that can conduct or show a false reading. R22 is one of those. It's a rarity, but when it does happen, it can kind of blow your mind. Maybe a perfectly good motor, and you're like, what's that thing like that for? But anything that's under 150,000 ohms, be suspicious. Okay. You know, if you got 5 ohms to ground, you got a problem. Okay. Any questions? Okay. I think that's going to conclude this part, and we'll move on from there. Thank you.